Welcome to AR Maths Pro Learning Academy. In this video, I'm gonna talk about Class 12 Mathematics, Chapter 1, Relations and Functions. Exercise Miscellaneous Questions from 1 till 7. Question 1. Show that the function f from R to x belongs to R, where x lies in between -1 to 1. Defined by the function f of x is equal 1 over 1 plus mod x, and x belongs to R, is 1, 1 and on 2. So we have to show that this given function is 1, 1 and on 2. At first, given function from my domain is all real numbers, and my range is x, which lies in between all real numbers from -1 to 1. Defined by the function f of x is equal x over 1 plus mod x. Here, mod x is positive whenever x is greater than or equal 0. And here x is negative when x is less than 0. So we take x positive if x is greater than or equal to 0. We take x negative when x is less than 0. Now we have some cases. At first, I took two elements from set A. For example, I took two elements from set A, which is x1 and x2. And I'm saying x1 is greater than or equal to 0 and x2 is also greater than or equal to 0, which means x1 and x2 are positive numbers. And they are, if I'm saying let x1 and x2 belongs to R such that f of x1 is equal to f of x2, which means f of x1 and f of x2 are only one term. If I make these two terms x1 and x2 are equal, if I make these two terms x1 and x2 equal, then it is a 1, 1 function. Let us check. Now f of x1 means x1 is greater than or equal to 0, so I will take x as positive. So in the given function is this one, f of x is equal to x over 1 plus x. I took positive x because x1 is greater than 0, greater than or equal to 0, as well as x2 is greater than or equal to 0. So I'm going to take this value only for both x1 and x2. It is like this: x1 over 1 plus x1 is equal x2 over 1 plus x2. x1 is this one, f of x2 is this one. By cross multiplying, x1 multiplied by 1 plus x2 equal x2 times 1 plus x1, like this. Now x1 has to multiply with 1 and x2, and x2 multiplied by 1 multiplied by x2. It will be like this: x1 plus x1 x2 equal x2 plus x2 x1. Now these two terms are the same on different sides, so you can cross out, because if I switch one term to the other side, it becomes negative and it becomes 0. So at this moment I'm going to cross out. So the remaining is x1 is equal x2. Check, I told you, if x1 is equal x2, which means there is only one image from x1 equal x2 to f1 f2. So the given function is 1, 1 based on this case. In the second case, I'm going to take x1 and x2 are less than 0. So these two terms are negative. Same thing, if x1 and x2 are less than 0, and if x1 and x2 are equal, then I will make only one image in set B, then it is a 1, 1 function. Let us check. Let x1 and x2 belongs to R such that f of x1 is equal to f of x2. Here I am going to take f of x1 value as negative since x1 and x2 are less than 0. So all x1 and x2 are negative numbers. I told you if x is less than 0, I will take negative x. So that's why I took in the function x as negative x. Here in place of mod x, I wrote negative x. So f of x1 is x1 over 1 minus x1 is equal x2 over 1 minus x2. Now on cross multiplying, x1 times 1 and x1 times x2, x2 times 1 and x2 times x1. If I multiply like this, I got this one. and both sides has the same terms, negative x1 x2, negative x1 x2, and negative x2 x1, same terms. So if I switch one term to the other side, it becomes positive. So and positive negative gets cancelled. And here I got x1 is equal x2, which means this is only one term and which has one image to f1 f2. That means the given function is 1 1. Before we start for the case 3, the given function I would like to write, and then mod x is this one. I am going to suppose to take, if x is greater than or equal to 0, I'm going to take this one. If x is less than 0, I'm going to take this one. Now, case 3. In case 3, x1, I choose x1 as greater than or equal to 0. So I will take this value from the function. And x2 is less than 0. So I will take this one. Now, try to understand. Since x1 is not equal as x2, since x1 is not equal to x2. Why they are not equal? Because one value is greater than 0, x1 is greater than 0, and x2 is less than 0. So they cannot be equal. So I have to show that it has two different images. This is for f of x1 and this is for f of x2. Then my function is 1 1. Then only my function is 1 1. In the previous cases, I said f1 and f2 are one element in set B. So I made it x1 and x2 equal. But in this one, they are different. They are not equal. x1 and x2 are not equal, which is at the beginning of the case 3 I already informed. So x1 is not equal x2, which means f of 1. What is f of 1? What is f of x1? Positive. I'll take this value. Now, if I plug in any values of x1 as positive, yani if I take 1, 2, 3, any numbers, the result is getting positive number only. Check. If I take 1, so 1 over 1 plus 1, 1 over 2, 0.5, which is greater than 0. Right? So if I take any positive values of x, I am getting greater than 0. So f of x1 is greater than 0 or equal 0 or greater, because if I choose x is 0, x1 as 0, so I get 0. In the same way, if I choose x2 as less than 0 means it could be negative 1, negative 0.1, negative 1.5, negative 2.5, something which is negative. So the given function is this one. In place of x2, if I write any negative values, the result is always negative. You can plug in any value, any negative value. If I write negative 1, I cannot write negative 1, of course, because 1 minus 1 will be 0, and you cannot write negative 1. You can write it. So if I write negative 1, it will be negative some value, negative half. Okay. So if you took 2, 3, any values, if you take any negative values, you will get the result as negative. So f of x2 is less than 0, always less than 0. So I have two different images. Check. For x1, I have different image, and for x2, I have different image, because f of x1 is greater than 0 and f of x2 is less than 0. So I have two different images, which means the given function is 1 1. They are not equal. Check. F of x1 is not equal to f of x2. Then it is a 1 1 function. In the same way, we can go through for the case 4. If x1 is less than 0 and x2 is greater than 0, if x1 is less than 0, which means I have to take the negative value, like this, x1, and plug in any negative values here, negative 1, negative 2, negative 3, I will get the result as negative. So f of x1 is less than 0, always. In the same way, if I choose x2 as 0 or more, then I have to take the function f of x as x over 1 plus x. Now, if I plug in any values, any positive values of x2, even if I plug in 0, I get 0. If I plug in 1, I get 0.5. So whatever you take, any real numbers, not real numbers, positive numbers greater than 0, I am getting more than 0, which means f of x2 must be greater than or equal to 0, whereas f of x1 is less than 0. So two elements of set A has two different images. Since f of x1 is not equal f of x2, then the given function is 1, 1. Therefore, from all the cases, all the four cases, we can conclude that the given function is 1, 1. For on2 function, in this function, let y is equal f of x. Then y equal this one. I will take x is greater than or equal to 0, I will take positive x. If it is less than 0, I will take negative x. Now, in this case, if x is greater than or equal to 0. Now, before we check for onto, the meaning of onto is set B, the elements of set B must have pre-images in set A. Then only we say it is an onto function. So for that one, I'm going to go for the reverse order. Reverse means I have to find the inverse of the given function. If x is greater than or equal to 0, y equal x over 1 plus x. If x is greater than or equal to 0, I take x as positive. So I took this one. From this function, solve for x. Solve for x means I have to cross multiply. This x plus 1 will cross multiply with y. So y times 1 plus x is equal x. And this y has to multiply with these two terms inside. So y plus xy is equal x. I will switch xy to the other side, it becomes negative. And from these two terms, I will take x as common. So it will be 1 minus y. I need y, solve for y. If I need y, I will divide 1 minus y on both sides. So x is equal y over 1 minus y. Now, what are the y values I am going to choose? What are the y values I am going to choose? So that x must be greater than or equal to 0. At first, I cannot choose y as 1 because it will be undefined. I cannot choose 1. Think about the numbers. If I took y as negative 1, so the result will be negative. I cannot take negative values also. So I cannot take negative 1. I cannot take 1. So it must be in between these two. Can I take 0? Yes, I can take 0y as 0. If y is 0, then x is 0. X is equal to 0, which satisfies. So y values, I can take 0 till 1. So y lies in between 0 and 1. Check, y lies in between 0 and 1. I can take any real numbers from 0 to 1 of y values. So that then these y values only, if I substitute in these y values in between these real numbers, I can get a pre-image. Otherwise, I won't get the pre-image. So y lies in between 0 to 1. In the same way, if x is less than 0, if x is less than 0, I am supposed to take this function x over 1 minus x, because x is less than 0. The same process. To know it is an onto function, every set B, elements of set B must have a pre-image. So solve for x from this given function, the denominator part 1 over x over 1 minus x, this cross multiplied with y. So y times 1 minus x is equal x, and this y will multiply inside the parenthesis. So y is equal, so y minus xy equal x. I switch negative xy to the other side, it becomes positive. And from this from this side, right side, choose x as common, then it will be 1 plus y. Divide 1 plus y on both sides. So x is equal to y over 1 plus y. Now, what are the y values I have to choose so that x is less than 0, sorry. Less than 0. So what are the y values I have to choose? Can I choose -1? I cannot choose -1. If I choose -1, it will be undefined. So -1, I cannot choose it, right? -1, I cannot choose it. Can I choose 0? If I choose 0, it will be 0. I cannot choose 0 also. In between them, choose any values. In between -1 and 0, choose any values, like 0.5, -0.5. I get negative x value as negative. So the y values, I can choose it from -1 to 0. Other than that one, I don't have pre-images of set B. So the y values must be in between -1 to 0 in this case, if x is less than 0. So in case 1, if x is greater than or equal to 0, y lies in between 0 to 1. In case 2, if x is less than 0, y lies in between -1 to 0. So the given function will be like this: y over 1 minus y, if y lies in between 0 to 1, and y lies in between -1. In general, I will say the given function is on 2. I will say given function is y belongs to R, such that y lies in between -1 till 1. -1 till 1. Then only the given function is on 2. Question 2. Show that the function f from R to R given by f of x is equal x power 3 is injective. Injective means 1, 1. Which means we have to show that the given function f of x is equal x power 3 is 1, 1. At first, the given function is y equal x power 3. The definition of 1, 1 says each element of set A of domain must have a unique and different image in set B. That's it. We have to prove this thing only. The given function is f of x is equal x cube, which means let xy belongs to R such that f of x is equal f of y. We know that if I have two elements, x and y, in set A in domain, and in set B I am saying f of x is equal f of y. Now we have to prove that these two elements of set A are equal. That's it. So f of x is x cube and f of y is y cube. X cube is equal y cube. Now remember this note. If x cube is equal y cube, yani odd powers. If I have odd powers and xy belongs to real numbers or natural numbers, whatever so, okay, then x is equal y directly. X is equal y. So I'm saying x is equal y. If x is equal y, which means the given function is 1, 1. So the given function is injective. F of x is equal x cube is injective. Please make a note. Injective means 1, 1 and surjective means on 2. 3. Given a non-empty set x, consider P of x. P of x is the power set of all subsets of x, defined by the relation R in P of x as follows. For subsets A, B in P of x, A or B, which means A relates B, if and only if A is the subset of B. Is R an equivalence relation on P of x? Justify your answer. At first, let me explain what is subset. Subset means, suppose I have x has 3 elements, 1, 2, 3. Okay, then 1 is the subset of set X, 2 is the subset of set X, 3 is the subset of X, like this. First of all, what is given? Let us imagine X has 2 elements, okay? Then its power set is phi, set A, set B, and set AB. And it is also given that relation P to P, which means subsets A, B in P of X, then A relates B. It is given if and only if A is the subset of B. A is the subset of B means A comma B belongs to R. If A relates B, the meaning of this one is A comma B belongs to R, if and only if A is the subset of B. This is the given definition. To know whether the given relation is equivalence, we have to show that it is reflexive, symmetric, and transitive. What is reflexive relation? Reflexive relation defines for any A belongs to A, we have to show that A comma A belongs to R. Let A belongs to power set. Of course, A is the subset of X, okay? And if A belongs to P of X, which means A is the subset of A. Why I am saying? Because every set is a subset of itself. We know this one. Every set is a subset of itself. If A is a subset of A, which means A is related to A. A or A. If A or A, the meaning is if A or B, if A is the subset of B, then A relates B. A is the subset of A, which means A relates A, which means A comma A belongs to R. If I show that A comma A belongs to R, which means the given relation is reflexive. For symmetric, the definition of symmetric says if A comma B belongs to R, then B comma A must be belongs to R. Let A comma B belongs to power set. If A comma B belongs to power set, which means A is related to B if and only if A is the subset of B. Now, if A is the subset of B, then B cannot be the subset of A. If I am saying A is the subset of B, then I cannot say B is the subset of A. Not possible. So if B is not the subset of A, that means B comma A does not belongs to R, which means the given relation is not symmetric. For transitive, the definition of the transitive says if A comma B belongs to R and B comma C belongs to R, then AC must be belongs to R. This is the definition of the transitive. Let A comma B belongs to power set and B comma C belongs to power set. If A comma B belongs to power set, which means A is the subset of B, and if B comma C belongs to power set, that means B is the subset of C. It should be like this. Now it is clear, if A is the subset of B and B is the subset of C, it is clear that A is the subset of C, of course. A is the subset of C. If A is the subset of C, which means A relates C. A relates C, which means A comma C belongs to R. Therefore, the given relation is transitive. So, the given relation is reflexive and transitive, but not symmetric. Hence, given relation R is not equivalence relation, since it is not a symmetric relation. Question 4. Find the number of all onto functions from the set 1, 2, 3, so on till n to itself. At first, these are the sets, okay? To itself means set A and set B are the same, okay? What is given? Set A and function f from A to A. Now, we should know that every element of codomain or set B elements must have a pre-image. So 1 has many options to be a pre-image of set A. Means 1 could be a pre-image of 1, 1 could be a pre-image of 2, 1 could be a pre-image of 3, 4, and so on, like this. So 1 has number of options, n terms. That's why I said 1 belongs to set A, which is codomain, okay, has n elements in set A. Okay, so we have n options for element 1 of codomain. Similarly, for element 2 of codomain, it has one option less than element 1, because 1 already took one pre-image. So the second element has less than one opportunity to be a pre-image. So it could be 2, 3, 4, so on. So pre-image of 2, which belongs to domain, has n-1 elements in set A, which is domain. In the same way, 3 has n-2 elements, because already these two elements has one images. So 3 has n-2 elements. In this way, we can find the total number of functions, the total number of onto functions, like this. So 1 has n elements, the second element 2 has n-1, 3 has n-2, and so on. It goes like 3 to 1, which means the total number of onto functions are n factorial. Question 5. Set A has 4 elements and set B has 4 elements. And function f and g from A to B defined by f of x is equal x square minus x, and g of x is equal 2 mod x minus 1 over x minus 1, where x belongs to A. We have to check whether the function f and g are equal and justify your answer. At first, what is given I will write. Set A has 4 elements, -1, 0, 1, 2, and set B has 4 elements, -1, -4, -2, 0, 2. And the functions are defined by f of x is equal x square minus 1 and g of x is equal 2 mod x minus 1, x minus half minus 1. Now, we have to find each element. First of all, for set A, f of minus 1. F of minus 1, function f of minus 1, I will take this definition. Okay, f of x is equal x square minus 1. So in place of x, I will write -1. Okay, so if it is -1, it will be like this, -1 power 2 minus, and in place of x, I will write -1. So -1 power 2 will be +1, and here +1, which is 2. So f of -1 value is 2. In the same way, I will find g of -1. G of -1, I have to take g of x as this one. G of x is equal 2 mod x minus half minus 1. So in place of x, I will write -1, like this. Check, in place of x, I wrote -1. By solving this in the denominator as 1, I solved this one. I got as -3 over 2. Okay, and modulus of -3 over 2 is positive. Mod of -3 over 2 is positive. And here, 2 and 2 cross out, and 3 minus 1 will be 2. So g of -1 is 2, and f of -1 is also 2, which means f of -1 is equal g of -1. Similarly, in the second part, I have to find f circle g, f of 0. And we know f of x is defined by x square minus x. So in this case, I will write, in place of x, I will write 0. Okay, so 0 square minus 0 is nothing but 0. So f of 0 is 0. Now find g of x. And g of x is defined by 2 modulus of x minus 1 minus half minus 1. In place of x, I will write 0. Okay, 0 minus half is minus half. Mod of minus half is half. So 2 and 2 cross out, numerator and denominator, and 1 minus 1 will be 0. So f of 0 is 0 and g of 0 is also 0, which means f of 0 is equal to g of 0. The third element. The third element says f of 1. F of 1 means in place of x, I will write 1. Okay, f of 1. 1 square minus 1. 1 square minus 1 is nothing but 1 minus 1, which is 0. Again, f of 1 is 0. Okay. The second part, I will go for g of 1. G of 1, in place of x, I will write 1. So 1 minus half is half, positive half. So g of positive half. Mod of positive half is positive half only. It will be 2 times 1 over 2. And numerator 2 and denominator 2 I can cross out, which means 1 minus 1, again it is 0. G of 1 is 0 and f of 1 is also 0, which means f of 1 is equal g of 1. Now, the fourth part, f of 2. In place of x, I will write 2. It will be 2 square minus 2. In this function, I'm going to plug in this f of 2 in this function. 2. If I plug in 2 here, 2 power 2 is 4, minus 2, it is 2. 4 minus 2, it is 2. So f of 2 is 2. Now, g of 2 means in place of x, I will write 2. In place of x, I will write 2, like this. So in place of x, I wrote 2. So 2 minus half is nothing but 3 over 2, mod of 3 over 2. Mod of 3 over 2 is mod of 3 over 2 only. And here, numerator and denominator, you can cross out 2 and 2. And 3 minus 1 is 2. Now, g of 2 is 2 and f of 2 is also 2, which means f of 2 is equal g of 2. So, what we justify? We justified that function f is equal function g. Question 6. Let set A has 1, 2, 3 elements. Then the number of relations containing 1, 2 and 1, 3, which are reflexive and symmetric but not transitive. So we have to make a relation by using this set A, so that relation must be reflexive and symmetric only, but not transitive. First of all, the given set A has 3 elements, 1, 2, 3. So we have to find the Cartesian product of the given set, which is this one. 1, 1, 1, 2, 1, 3, and 2, 1, 2, 2, 2, 3, and 3, 1, 3, 2, 3, 3. This is the Cartesian product. From this Cartesian product, we have to make relations so that relation must be reflexive and symmetric only. So at first, I am going to consider all ordered pair with the same elements, 1, 1, 2, 2, and 3, 3. Because all these ordered pair with the same elements satisfies reflexive, symmetric, and transitive relation. Now, it is given that the relation must contain these two sets, 1, 2, and 1, 3. That's why I wrote 1, 2, and 1, 3. To show that this 1 2 and 2 3 is reflexive, if 1 2 is there, then it must be 2 1, and if 1 3 is there, it must be 3 1. Now this relation is reflexive because it has 3 ordered pair elements with all the elements, same elements, okay, and symmetric. We have to check whether the given sets, whether the given relation is transitive or not. So I don't need to check for these because this satisfies transitive. Now check with this one, 1 2 2 1 and 1 1 is there, yes, and 1 2 2 2 is there and 1 2 is also there. So this satisfies the transitive relation. Check with the third one, with this one, 1 3 1 3. Okay, now check. I'm just writing one example for you. 1 3 and 3 1, 1 3 and 3 1, which means 1 1 must be there. It is there. Check, 1 1 is there. And 1 3 1 3 3 3, 1 3 and 3 3, which means 1 3 must be there, right? 1 3 is also there. So this ordered pair satisfies transitive relation. Check with the second last one, 2 1 2 1 and 1 1 is there, 2 1 and 1 1 is there, which means 2 1 must be there. Yes, it is here. Check. And 2 1 1 2 is there. You mean 1 2 2 2 must be there. Yes, it is here. So this is also satisfied transitive test. Now check with this one, 3 1 and 1 1 is there, which means 3 1 is there. Yes, it is there. 3 1 and 1 2 is there, which means 3 2 I have to check, and 3 2 is not there in this relation. So this is not transitive. So this relation is reflexive and symmetric but not transitive. In the same way, I have to check another relation. Up to here, yes, it is not there. The remaining two parts is there. Two elements is there. 2 3 and 3 2 is there. So I have to take 2 3 first. To make this reflexive, to make this symmetric, sorry, I must take 3 2 because opposite must be there. So this satisfied reflexive. Now up to here all these satisfied transitive. I have to check for these three only. Transitive. 3 1 1 1, any 3 1 is there. Yes. 3 1 1 3 3 3 is there. Yes. 3 1 1 2 and 3 2 is there. Yes. So this satisfies transitivity test. 2 3 and 3 3, which means 2 3 is there. Yes. 2 3 and 2 1, 2 3 and 2 1, which means 2 1 is there. Yes, it is here. 2 3 and 3 1, which means 2 1 is there. Yes, 2 1 is here. So this is also satisfies transitive test. 3 2 and 2 2, which means 3 2 must be there. Yes, it is here. 3 2 and 2 3 and 3 3 must be there. Yes, it is here. So all these elements satisfies transitivity test. So this relation is symmetric, transitive and reflexive, but we don't need transitive. So this I don't consider this one. So we have only one relation, which is reflexive and symmetric but not transitive. So the answer is option A. Question 7. Set A has 3 elements, 1 2 3. Then the number of equivalence relations. By using this set, how many equivalence relations I can make it? Remember, equivalence relation means symmetric, transitive, and reflexive, all three, which must contain this set 1, 2. Now, what is given set 1, 2, 3, set A? We have to find the Cartesian product, which means all ordered pair. And in this one, I'm going to consider first relation. I'm saying name as R1, which has 1, 1, 2, 2, 3, 3. This satisfies reflexive relation. Okay. And in this relation, 1, 2 must be there. So 1, 2 is there. So 2, 1 must be there to show that this relation is symmetric. Now I have to check transitive. So for the first 3 ordered pair, I don't need to check because doublets satisfies the equivalence relation, which means these 3 sets is reflexive, symmetric, and transitive. Now I have to check the third one, fourth ordered pair. 1, 2, 2, 1, 1, 1 must be there. It is there. Check. 1, 2, 2, 2, which means 1, 2 must be there. It is here. So this satisfies transitivity test. 2, 1, 2, 1, and 1, 1, which means 2, 1 must be there. Yes, it is here. 2, 1. 2, 1, 2, 1, and 1, 2, which means 2, 2 must be there. It is here. Check. So this also satisfies transitivity test. So this relation is equivalence, which satisfies reflexive, symmetric, and transitive. Now check another one. Already we know this is symmetric, reflexive, and transitive, which is equivalence. Now consider the rest of them, which means I have to take 2, 3. If I take 1, 3, sorry, I forgot this one. 1, 3. To make it symmetric, I have to take 3, 1. To make it symmetric, I have to take 3, 1. In this way, I have to take 2, 3, and then to make it symmetric, I have to take 3, 2. Now, if you see this relation, it is a Cartesian product. And remember, always a Cartesian product satisfies all the all the relations, reflexive, symmetric, and transitive. So this relation is also an equivalence relation. So I can make only 2 relations based on this set. So the answer is option B. This is the end of miscellaneous exercise as well as end of the chapter relations and functions. If you have learned something new today, hit the like button, share with your friends and family, and don't forget to subscribe. Thank you so much.